Hello and good afternoon. This presentation will provide an overview of an automated scanning system we are developing at the Center for Fine Print Research, UWI, in Bristol, to acquire image data to record textured planar surfaces like paintings. The presentation will demonstrate the scanner through a case study of a painting by Italian artist Canaletto, the Grand Canal Ascension Day. This project is a collaboration with my CFPR colleague Thomas Bale and Kyle and Chet from Bashtu, a technology company working at the intersection of arts and robotics. So, in the next slides, I will explain where the idea of developing the scanner came from. I will explain the scanner and the application that controls it. I will introduce the painting we scan and how we did it. And then I will move to the processing of the data and I'll show you the results. Finally, I will mention briefly what we are currently working on. In early research, I studied various methods to record texture from paintings and how I could generate 3D models for online engagement that would be computationally efficient. To do so, I looked into photogrammetry as an affordable solution. However, where the limitations of photogrammetry would not allow the recording of fine detail, I would use surface normal maps produced with reflectance transformation imaging and incorporate those into 3D models. In this way, I could produce detailed 3D models as the one you see in the video. Even if the results were quite good, the process of capturing the images manually was slow, and sometimes certain regions wouldn't have enough data, and I would have to go back and take more photographs. Also, incorporating RTI normals would require registration to the 3D model, which in some cases was difficult to achieve. So the system we present here allows for automatic capture of images for both techniques, which provides perfect overlap, intrinsic registration, and high-resolution data. With this approach, we produce 2D and 3D data outputs for various applications. For example, for documentation of artworks, to record brushwork and monitor surface features, or for reproduction purposes, such as the generation of photorealistic 3D digital models and 3D printed outputs for tactile experience. Just before I explain the scanner, I thought it might be useful to briefly explain normal maps and how I use them in this project. Normal maps are 2D images or textures used in computer graphics which store a direction for each pixel, the normal. Each pixel in the image stores the x, y, and z coordinates of that angle represented in RGB values. With this information, 3D software can create the illusion of texture when the image is illuminated. They are normally used to fake high-resolution detail when mapped onto low-detail meshes, as in the previous video. One way to generate these normal maps is by using reflectance transformation imaging, by photographing a surface multiple times from the same point of view, but with different light directions. In the example above, the panel painting had one normal map only for the painted surface at the front. The rest were generated with photogrammetry. Now, with the scanner, we can record multiple RTIs of the whole surface, merge them together, and produce a very detailed record of that surface, in this case, Canaletto's painting. The prototype scanner is designed to capture the color and structure of planar surfaces. The design offers an affordable and simple solution to acquire image data. The cost for all the materials was just under £1,200, excluding the camera. The system uses a digital camera. In this case, we used the Sony Alpha A7R Mark II with a Sony 50mm lens. The camera is coupled to LED screw linear actuators placed perpendicularly on a 1 meter by 1 meter extruded aluminum frame. The system allows the recording of all necessary image sets automatically and seamlessly, reducing the capture time. The scanner can record an area of about 1 meter square, but it can record larger areas by using a rail system to scan consecutive sections horizontally and by raising or lowering the rig to scan sections vertically, as in the case of Canaletto's painting. The RTI part, the dome, has 24 LEDs, 3 LEDs in each spoke. The spokes are extendable in case the area being recorded requires a larger field of view, so the LEDs can be positioned to the correct distance. The camera sits in the center and can be tilted up and down to improve the positioning of the camera in reference to the surface being scanned. The software interface to control the scanner has three modes: photogrammetry, RTI, and a combination of both. First, the user inputs the field of view of the camera, the point of origin, the size of the area to scan, and the overlap between images required. The app then calculates the overlap and shows a preview of all camera positions. The user can also choose the power of the LEDs and the camera parameters. And we added an option called shake time, which is basically the time the system waits to shoot the next picture after moving to the next new position. In this way, we avoid any possible vibrations while recording. The user can also select specified LED combinations to check that the camera parameters are correct with the LEDs at different angles. Once ready, the system is triggered and records all the necessary images. To demonstrate the results, we scan this painting by Canaletto. The painting is an oil on canvas and depicts the view of the Bacino di San Marco. The painting illustrates the Ascension Day festivity, which celebrates the union of the city with the Adriatic Sea through a symbolic marriage ceremony in which the Doge, the chief of state, cast a blessed golden ring into the waters. The painting, housed at Woburn Abbey, had just undergone a restoration at Bristol-based art conservation studio IFAX, in preparation for an upcoming exhibition at Holborn Museum in Bath this year, hopefully. This painting was a good candidate to demonstrate the scanner, not only because of its size, but because of the apparent lack of surface texture when compared to other artists, which might present a richer paint application. The painting was placed on a wooden easel, secured from the back in a dark area of the studio. Darkness is necessary to avoid external lighting from interfering with the capture and quality of the images. A set of scale bars were placed at the bottom of the easel with known distances to later calibrate the 3D data. A color checker passport was used for color calibration, and a custom calibrated height reference board was also included in the capture to use later during RTI normals calibration. The photogrammetry sequence was captured using 4 LEDs to obtain even lighting in the field of view, although we might use a LED ring in the future to produce better diffuse lighting. Before the RTI sequence started, we calibrated the light positions with the black billiard ball system, often used with the highlight RTI method. The painting required 6 sections to be fully recorded, and each section overlapped with its adjacent ones to maintain the necessary overlap to process the data. The painting was highly specular, as the recording was done just after fresh application of varnish, as part of the conservation treatment. This, I think, also caused a couple of issues I will mention later. The recording of the painting took 4 days, including setup and disassembly, and a 2-hour-long break when the scanner decided to stop working. You can actually see a missing row of images that I missed when the scanner stopped working, although these didn't affect the processing as there was plenty of overlap. And for anyone interested in the numbers, photogrammetry consisted of 2,200 images, the white dots on the top left image, and 110 RTI images, the red dots. And the RTI consisted of 110 sets of 24 images, which is 2,640 images in total. Here we have a chart to briefly explain the processing workflow, although in the coming months we will be finalizing our own custom application to process the RTI images. This will allow us to use TIFF images instead of JPEGs and calibrate the normals correctly. So on the left we have photogrammetry. In this case I've used Agisoft Metashape to process the images. These have been exported from RAW to 16-bit TIFF. On the right, the RTI images are exported as both JPEGs and TIFFs. The JPEGs were processed with the well-known RTI builder, and then each normal map was exported from each RTI set with the RTI viewer. The TIFF images are used to produce an image with average color from each RTI set. These are then incorporated into the photogrammetry set for processing, so they are registered and calibrated. This allows later in the process to either use the color images to process color textures, or the RTI normal maps to produce mosaicked normal maps. Once the point cloud is obtained, we can generate and export a digital elevation model orthomosaics, and a 3D mesh ready for optimization and texturings, which I will show you in the next slides. Here we have the three types of data produced. A digital elevation model, which are raster representations in 3 dimensions and usually used to quantify the characteristics of the surface of the Earth. But they are incredibly useful to quantify surfaces like paintings. You can see at the bottom left image an example, the measurement of the profile of a small section of the paint surface. We also produce 2 orthomosaics combining all available images, 1 color image and 1 normal map. Both images with a spatial resolution just above 900 dpi or 350 points per centimeter. You may be able to see the color and a shaded render of the normals online soon as part of the Holborn Museum exhibition with a zoomable image viewer. And finally, we produced a high polygonal mesh, which is then optimized externally and imported back into Agisoft to map the color information and the RTI normal maps to generate the 3D model. I have actually uploaded a 3D model to Sketchfab, although for some reason the RTI normals were not rendering correctly, so I used the photogrammetry normals instead. Also, the model is not optimized for mobile devices, as I wanted to keep as much detail as possible. I would also recommend to see it in HD quality, as in SD, Sketchfab messes up textures. The RTI processing also provides a good record of the surface. As mentioned earlier, for this painting, we produced 110 RTI separate sections. Although the information is in individual sections, you can still use the viewers to inspect the section of the painting that you're interested in. Now I will show you a few slides comparing the surface texture recorded with photogrammetry as a grayscale DEM and a shaded render of the RTI normals orthomosaic. Each section is 9 centimeters square. This one shows the Ducal Palace. You can see how good is the quality of the detail produced with photogrammetry on the right side. However, RTI normals are still superior when recording finer brushwork. You can also see the nice incision marks on the architecture Canaletto did when preparing the painting. Here we have part of the clouds. See how the RTI normals managed to record the canvas width and some of the finer brushwork as well. I also wonder if the fresh application of varnish may have caused a bit of softening of the surface, mostly on the photogrammetry side, maybe due to the scattering of light. I'm not sure. Although this may be difficult to see in your screen. This slide shows part of the Church of La Salute. Again, both techniques managed to recover a good level of detail, but RTI was better with the finer features. Also, there you see, because the varnish was fresh, little dust particles remain on the surface of the painting, and even though the conservator tried to remove most of them, photogrammetry picked all those up. Fortunately, RTI didn't, and you will see that in the next video. This video is just a recording of a Photoshop window, and it shows the color orthomosaic, the normal orthomosaic as a shaded render, and the DEM at the very end. You can see the scale or the ruler on top and left side too. I'm zooming into the Campanile, and I'll play with the transparency of the layers. So I'm switching now to the RTI normals. Switching back to color. I'll move now to the architecture, the Ducal Palace, where you will see the nice incisions Canaletto used to make to prepare the canvases. You can see them very well in the arcs. And now they're on the windows on top. And I'll move now to the other side to show you the Church of La Salute, where there is a very small pentimento, which is part of the drawing, the marks that he was doing, and then he changed his mind and moved part of the church a little bit. You can see it there. I'll just switch now to the RTI normals. And I'll try to find now one of the dust particles, just to show you how it looks in photogrammetry and how it looks in RTI normals. So I'm switching now to the photogrammetry DEM, and you can see it there in the middle. You can actually see them in the color images as well. It's quite sort of little white spots. Back to photogrammetry. Now I'll show you in RTI. You will see that they are not picked up. And now I'll switch to the color shaded DEM just to quickly show you. You'll see there's a slight curvature of the canvas in orange. That's only a few millimeters though, as the actual depth was calculated from the back of the stretcher. You can see as well some of the dust particles there. Okay. This is only a quick video render of the 3D model with the RTI normals I did with Blender. I rendered this fairly quickly for the presentation, so it doesn't show its full glory. Here, I try to show the surface texture by moving a light around. Hopefully you can see that a little bit in your screen. This is obviously without the color, now back with the color. And that will be it. Okay. Right, so the last couple of slides, I'll move to explain our current work. We are now mostly developing the RTI workflow so we can customize the software and produce much better results, much better outputs. We are focusing on the recovery, stitching, and merging of surface normals with a variety of surface reflectance algorithms. We're also working on the integration of the surface normals to recover depth maps so we can then use them for physical reproduction with 3D manufacturing methods. That would be 3D printing or CNC machining. And also working on the registration of the high resolution normals and depth maps to the photogrammetric mesh to increase the level of detail. So one of the most important aspects that we're working on is the calibration of the surface normals. Because normals are view dependent, we need to calibrate every pixel in both each section and as a whole once merged together. You can see an example here in this slide. We have almost achieved correct calibration between the two sections, but there's still some work to do. You can see there's a slight difference where they merge. So hopefully we'll solve that in the near future. And that's all. Just to thank everyone involved in this project, especially Warburg Navi for allowing us to scan the painting. And feel free to contact me if you have any questions or suggestions. Thank you.